On satellite maps, a wildfire stops looking like a local event. A gray-brown plume separates from the source, stretches for hundreds and sometimes thousands of kilometers, and moves toward places where there is no fire at all. In the summer of 2026, the Copernicus Atmosphere Monitoring Service, or CAMS, tracked smoke from major Canadian wildfires toward the Canadian Arctic and across the North Atlantic. In Siberia, smoke from subarctic fires was transported toward the Arctic Ocean. On a map, enormous distances separate the flames from the polar regions. For the atmosphere, that distance is not an impenetrable barrier. That is the paradox at the center of the story. A forest can burn thousands of kilometers from the Arctic Ocean, yet particles released by that fire can still reach the air above Arctic snow, clouds, sea ice, and open water. So what actually happens when wildfire smoke reaches the Arctic? There is no one-line answer. The story is built from satellite observations, atmospheric models, field measurements, and decades of research into how particles move through the atmosphere. And the closer we look, the more complicated the answer becomes. The first thing to understand is scale. During the summer of 2026, several northern regions became important sources of large smoke plumes. CAMS reported major fires in Canada and significant fire activity in subarctic parts of Siberia, including Krasnoyarsk Krai. By late June and into July, smoke from these fires was already being tracked far from the places where it had been produced. Canada is especially important to the 2026 story. After a relatively quiet beginning to the boreal fire season, activity increased rapidly in late June. Large fires developed across several provinces and territories, many of them ignited by lightning. The Northwest Territories and Manitoba were among the areas with major fires. And later in July, intense activity also developed in Ontario and elsewhere. The smoke did not remain over the forests. CAMS tracked large Canadian plumes into the Canadian Arctic and out across the North Atlantic. That detail changes the scale of the event. Smoke was no longer simply a local consequence of burning vegetation. It had become an atmospheric phenomenon, capable of crossing regions and oceans. Russia showed a parallel process. Fires had already appeared in the Russian Far East in May, and larger fires developed in subarctic Siberia during June. Some of the resulting smoke was transported toward the Arctic Ocean. And here, the 2026 season produces an interesting contradiction. Globally, the first half of the year was unusually quiet in terms of biomass burning emissions. According to CAMS and its Global Fire Assimilation System, or GFAS, estimated global emissions from biomass burning between January and the end of June were the lowest in the dataset that begins in 2003. But a low global total does not mean that every region is quiet. A global number can hide intense regional episodes. While the worldwide total remained low, individual fires in Canada and Siberia were still powerful enough to produce smoke plumes that could be tracked over enormous distances and into high northern latitudes. That distinction matters. The atmosphere responds to where emissions occur, how intense they are, how high smoke is injected, and what the winds are doing at that moment. A relatively quiet year globally can still contain remarkable regional events. To understand how a fire in the boreal forest can become haze above polar ice, we have to follow the smoke from the beginning. When a large forest burns, the fire releases enormous amounts of heat. Air directly above the flames warms, becomes buoyant, and rises. That rising air carries smoke, gases, ash, and water vapor with it. For a smaller or smoldering fire, much of the smoke can remain relatively close to the surface. There it may spread through the lower atmosphere, become diluted, be removed by precipitation, or settle not far from its source. An intense wildfire can behave very differently. Strong heating can create powerful convective columns that lift smoke several kilometers into the atmosphere. In the most extreme cases, fires can generate pyrocumulonimbus clouds, often called pyro-CB clouds. These are deep convective storms driven by the heat of the fire itself. They can carry smoke, ash, and moisture high into the troposphere and, in exceptional events, even into the lower stratosphere. At that point, the smoke enters a very different transportation system. Winds near the surface may push smoke in one direction, while winds several kilometers above the ground move in another. Once smoke reaches higher levels, it can become embedded in large-scale atmospheric circulation. Cyclones, anticyclones, frontal systems, and fast upper-level winds can stretch a plume, bend it around weather systems, and carry it thousands of kilometers from its source. This is why the first minutes of a plume's movement tell us very little about where that smoke may eventually go. A plume can begin as a dense column above a burning forest. Hours later, it may become a broad, elevated layer. Days later, it may be a thin ribbon of aerosol moving over tundra, ocean, clouds, or ice. During that journey, the plume is constantly changing. Its particles mix with cleaner air. Some are removed by rain or snow. Some settle toward the surface. Some remain suspended for much longer. The plume stretches, thins, fragments, and can eventually become so diffuse that it is difficult to identify in ordinary imagery. But before that happens, modern observing systems can follow much of its journey. This is where satellites become central to the story. There is no single satellite instrument that sees everything about wildfire smoke. Different sensors measure different properties. Some detect active fires and the thermal energy released by them. Others observe how aerosols affect light passing through the atmosphere. Some instruments can provide information about the vertical structure of aerosol layers. CAMS combines satellite observations with atmospheric modeling to create a more continuous picture of where smoke is and where it may travel next. One of the important concepts is aerosol optical depth. In simple terms, it describes how strongly particles suspended in the atmosphere reduce the amount of light passing through an atmospheric column. A higher aerosol optical depth can indicate a larger amount of aerosol between the surface and the observing instrument, although interpreting the exact composition and altitude of that aerosol requires additional information. GFAS approaches the problem from the fire itself. It uses satellite observations of active fires, including fire radiative power, to estimate emissions. Those estimated emissions can then be introduced into atmospheric models that calculate how smoke and its components are transported. This combination of observation and modeling is powerful because satellite imagery always has limitations. Clouds can hide smoke beneath them. Viewing geometry and lighting conditions affect what optical instruments can detect. A single satellite pass is also only a snapshot. Models help connect those snapshots in time and space. But models are not magic, and satellites are not all-seeing. They are tools with different strengths and uncertainties. The most reliable picture comes from combining multiple observing systems with models and, where possible, measurements taken directly in the atmosphere or at the surface. And that brings us back to the Arctic. Why does smoke arriving there attract so much scientific attention? Part of the answer is simply that the Arctic has relatively few large local sources of combustion compared with heavily populated industrial regions farther south. Yet its atmosphere is not isolated. Air masses can transport pollution and wildfire products from North America, Eurasia, and other regions into the high north. That means Arctic air can contain the fingerprints of events that happened thousands of kilometers away. The second reason is the surface itself. The Arctic contains vast areas of snow and ice, surfaces that interact with sunlight very differently from dark forests, soil, or open ocean. This makes the region especially sensitive to anything that changes how solar energy is reflected, absorbed, or redistributed. Wildfire smoke is not one substance. It is a complicated mixture of gases and particles. For this story, two broad categories are especially important: organic aerosol and black carbon. Black carbon is essentially soot produced by incomplete combustion. It is very effective at absorbing sunlight. Organic aerosol often interacts with radiation differently, and some components primarily scatter incoming light. Other light-absorbing organic material, sometimes called brown carbon, adds another layer of complexity. This is why the phrase, "smoke warms the Arctic," is too simple. A smoke plume can both absorb and scatter radiation. Its effect depends on its composition, altitude, age, the clouds around it, the angle of the sun, and the surface below. A plume above dark open water does not interact with the radiation field in exactly the same way as the same plume above bright snow or a reflective cloud deck. Even the vertical position of the smoke matters. Aerosol above clouds can produce a different radiative effect from aerosol below clouds. So the immediate atmospheric effect of smoke cannot be reduced to a universal equation in which more smoke automatically means more warming or more cooling. There is, however, another pathway that is easier to visualize. It begins when light-absorbing particles reach the surface. Fresh snow is one of the most reflective natural surfaces on Earth. A large fraction of incoming sunlight can be reflected back rather than absorbed. This property is described by a term called albedo. Dark impurities can change that balance. If black carbon or other light-absorbing particles are deposited onto snow or ice, they can reduce the surface's reflectivity. The change may be tiny at the scale of an individual particle, but the physical mechanism is straightforward. A darker impurity absorbs more solar energy than the bright snow surrounding it. Research has shown that black carbon deposited on snow and ice is one mechanism capable of affecting the energy balance of cryospheric surfaces. But this is also where we have to be especially careful with the 2026 event. Seeing smoke above the Arctic does not prove that a particular plume deposited enough black carbon onto a particular ice surface to produce a measurable increase in melting. Those are different questions. Tracking smoke through the atmosphere tells us where an aerosol layer travels. Determining what reaches the ground requires additional evidence. Scientists may need surface measurements, snow samples, deposition estimates, chemical analysis, and comparisons across time. A plume can pass over sea ice without most of its particles ever reaching the surface. Some particles remain suspended. Some are removed before arriving. Some are washed out by rain or snow. Others may settle over ocean, tundra, or snow, depending on the weather along the route. So when we talk about black carbon and Arctic snow, we are talking about a well-established physical mechanism, not automatically claiming that every smoke event produces a large, measurable surface response. And the surface is only one part of the story. Smoke can also interact with clouds. Cloud droplets do not usually form from water vapor alone. They form around tiny airborne particles known as cloud condensation nuclei. Aerosol particles can provide those microscopic surfaces. Change the number and properties of particles in an air mass, and under the right conditions, you can change the number and size of cloud droplets. That can influence cloud brightness, lifetime, precipitation, and the way a cloud interacts with radiation. But again, the word "can" matters. More aerosol does not automatically create more cloud. Smoke does not guarantee warming, and it does not guarantee cooling. The result depends on humidity, temperature, cloud type, aerosol chemistry, atmospheric stability, and many other factors. Aerosol-cloud interaction remains one of the more complicated parts of atmospheric science. The Arctic makes this question particularly interesting because some Arctic air masses can be relatively clean compared with polluted continental environments. In cleaner conditions, an influx of additional particles can represent a larger relative change in the available aerosol population. That does not mean the climatic effect must be large. It means the signal can be scientifically valuable. Researchers have been studying this long-distance connection for decades. Long before today's satellite networks, observers in the Arctic noticed a persistent haze that seemed strange for such a remote region. The phenomenon became known as Arctic haze. Scientists eventually established that pollutants could be transported into the Arctic from much farther south. Industrial emissions, combustion products, and other aerosols can enter large-scale circulation and travel across national borders and entire continents. Wildfire smoke is part of that broader story of long-range transport. The modern difference is visibility. Decades ago, researchers often had to rely on aircraft campaigns, ground stations, filters, and direct sampling to determine what was present in Arctic air. Those methods are still essential, especially when scientists need chemical composition or precise surface measurements. But today they are joined by satellites and global atmospheric models that can watch enormous regions at once. A plume that once might have been noticed only as a gray horizon can now be followed from its source across changing weather systems toward high latitudes. And the 2026 fire season offers a useful example of why this matters. During the first half of the year, global biomass burning emissions were at the lowest level in the GFAS record beginning in 2003. Yet by late June and July, major boreal fires were producing long smoke plumes in Canada and Siberia. In July, Canada became the largest national contributor to global wildfire emissions for that month in CAM's Fire Emissions Watch data. With widespread smoke transport across North America, the Canadian Arctic, and the North Atlantic. That is not a contradiction. It is a reminder that the global atmosphere is shaped by both totals and geography. A global annual statistic tells us how much was emitted overall. It does not tell us where the smoke went, how high it traveled, or what environment it entered. A single intense regional episode, combined with the right circulation pattern, can produce an atmospheric signal thousands of kilometers away. This is the more important lesson. The Arctic may look isolated on a physical map. It is surrounded by ocean, ice, tundra, and enormous distances. But in atmospheric terms, it is connected to the rest of the northern hemisphere every day. The air above the Arctic has a history. Some of it has passed over oceans. Some has crossed industrial regions. Some has traveled above forests. And during wildfire season, some can carry the chemical and physical traces of burning landscapes far to the south. That does not mean every plume changes the Arctic climate in a dramatic way. It means the Arctic is not protected by distance. To understand the effect of a particular smoke event, scientists have to separate several questions that are often blurred together. Where did the smoke originate? How high did it rise? Which atmospheric pathway carried it north? How much aerosol remained in the air when it reached high latitudes? What was the mixture of black carbon, organic aerosol, and other components? Did the particles remain aloft, interact with clouds, or reach the surface? And if deposition occurred, was it large enough to measurably change snow or ice reflectivity? Satellites can answer parts of those questions. Models can answer other parts. Aircraft, ground stations, and snow samples provide still more pieces. No single observation tells the entire story. That is why the image of a smoke plume over the Arctic is scientifically interesting, without needing to be turned into a catastrophe. The remarkable part is the connection itself. A fire burning in a remote forest can release particles into a rising column of air. Those particles can be captured by winds far above the ground, carried across lakes, tundra, coastlines, and ocean, mixed with clouds, diluted, transformed, removed, or transported farther still. Days later, some portion of that original plume may be present in air thousands of kilometers from the flames. The source and destination may belong to completely different landscapes, but they are connected by the same moving atmosphere. In the weeks ahead, satellites and atmospheric models will continue to show where new fires develop, where their smoke travels, and how far aerosol layers penetrate into northern latitudes. Field observations and laboratory analysis are needed to answer the harder question of what actually reaches Arctic snow and ice, and what effect that deposition may have. That distinction is essential. We can observe transport almost in real time. Understanding consequences takes longer. And perhaps that is the clearest way to think about the Arctic in the summer of 2026. Do not look at it as a sealed, white world at the top of the planet. Look at the atmosphere around it. Follow the winds southward across the ocean, over tundra, across the boreal forests of North America and Eurasia. Somewhere along those pathways, a fire may be burning thousands of kilometers away. And under the right atmospheric conditions, part of that fire can still reach the Arctic sky. Sometimes, to understand what is happening in the Arctic, you have to look far beyond the Arctic itself.